Okay, this is the ninth video in the playlist that deals with Lewis formulas, and we're going to deal with an advanced topic here, specifically called resonance. And resonance is a phenomenon where more than one, and this is a key word in this definition, more than one equivalent Lewis formula, and I'm going to abbreviate this as LF. All right, so more than one equivalent Lewis formula is possible for a given molecule. All right, and the model system that we're going to look at here is the nitrate molecule. So it's another polyanion, like sulfate, for example, except the difference is, and this is an important distinction, is that nitrogen, all right, is in period 2. So let me write my period numbers here going down the left side of this periodic table. So you see that nitrogen is in period 2, and the significance of that is that nitrogen does not have d orbitals that can be involved in the formation of bonds that lead to a molecule. All right, so it does not have d orbitals that can participate in bonding. So I want to start with this example because when we switch to sulfate, then things are a little bit more complicated. We got to talk about, you know, the use of formal charges and things like that that were introduced in the previous video. So let's go ahead and start. It's the usual thing. We're going to apply the steps. So nitrogen is in group 5, so we're going to have 5 valence electrons for the nitrogen. There's 3 oxygens, and oxygen is in group 6. And then we have a charge of -1 on the molecule that needs to be added on to this. So for nitrate, the valence electron budget is 24 electrons that we have to account for in the bonding. All right, and so let's proceed. We follow our steps. So the next thing that we're going to do is we're going to write a skeleton structure. All right, and if I didn't mention this, here is another aspect of the fact that nitrogen is in period 2. And that aspect is that nitrogen must abide by the octet rule. So we're not going to be violating the octet rule here. All right, so let's go through now and connect our atoms. And we see that we have we've used a total of 6 electrons. We have several to go, and well, you know what? I think I'll just go ahead and do this. So we're going to draw the structure incorrectly to begin with, so that we stay within the parameters of using the steps. So the next step here would be for me to add my electron pairs. All the way around on the oxygens. And then we would do our count. So it's going to be 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So you see this structure is not possible. So let me put our skeleton structure back. We're going to connect all the nitrogens. All right, and then what I'm going to do is add a double bond here. And that makes a total of 8 electrons on the nitrogen total. So now I'll go in and we'll do our electrons, our unshared pairs of electrons on the oxygens. All right, and I get all the way around on that. All right, and now let's do our count. So there's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So we've hit our magic number. All right, This correlates, the 24 correlates with what we started out with for valence. And a quick inspection indicates that there are 8 electrons around each of our respective atoms that are in the molecule. Now, what you're going to notice is that we could have put this double bond in either of 2 other locations and it would have made no difference. And what I want to do really quick is we're going to number the oxygens. So this is going to be number 1, this is going to be number 2, and this oxygen here we'll call number 3. All right, so we could have put the double bond at position 3 here, or we could have put it at position 2. So I'm going to go ahead and redraw the formula, taking that into account. So if we're not in position 1 with that double bond, I'll just put the 1 there to indicate that. Instead, we would be here with it at position 3. And then we're going to have, like we did in the other molecule, another single bonded oxygen at this position here. All right, and which is position number 2. All right, and we have a third option, therefore, and that's where we would have the double bond here at position number 2. All right, where the oxygens that are in the first position and the third position are single bonded. All right, now you can see when you compare all 3 structures that they are the same molecules except for where the double bond is positioned. So that word equivalent has to do with the fact that these are structures that are essentially identical except with the position of where the double bond is in the molecule. Now, we call this phenomenon resonance, and we use resonance to essentially explain the breakdown in the model that we utilize to draw structural diagrams of these particular molecules. All right, so what this indicates when we look at this is that some of the electrons that are involved in the bonding can actually exist in 3 different locations within this molecule. And so there is a concept called delocalization. And what this means is that electron density all right, in the double bond is dispersed over the surface area of the molecule. All right, so essentially nitrate doesn't really have a double bond in it. Some of the double bond character, a fraction of the double bond character, is split over all 3 bonds that are here. So in one sense of this, there's going to be about 1/3 double bond character for one-third double bond character for each of the multiple bonds in this case. In a sense, in one way of thinking about it, so that times 3 bonds is equal to 1. So essentially, some of that double bonded character is dispersed over the surface area of this molecule. And the idea here is that basically our model that we're utilizing to describe this molecule is not exactly right. Some of the electron character that's involved in the multiple bond character of the bonds that are in here is dispersed over the entire molecule. So we use resonance in order to modify our model to acknowledge the fact that for some molecules there can be more than one equivalent structure. And I think I'm going to close this video here.